So we have this guess for what we relationship that we think we might have between line integrals and a surface integral of the curl of the vector field when we have compatible orientations. But how could we actually prove this? I mean, if you think back to how we proved Green's theorem, we started out with a very special case where the region had a very simple form. We proved it for that simple form, and then we sort of put pieces together because along shared boundaries, the line integrals, we were traversing the shared portion of the boundaries twice, but in opposite directions, and so those parts zeroed out, or those parts canceled. We could use the same strategy for our guess here because this is still a line integral, so that same cancellation is going to happen. So the idea is, right, if we have some complicated surface, okay, we can split it into two pieces, or any number of pieces, right? So introduce these splits. This will give us two surfaces instead of one. So I'll call the one on the left S1 and the one on the right S2. And right, we have the old boundary is now made up of C1 and C2. And this new cut that we introduced is now a new part of a boundary. Let's call that C3. The integral over the entire surface, so the integral of the vector field over the entire surface at d sigma, is just the integral over S1 plus the integral over S2, right? Because S1 and S2 are different surfaces that don't that only overlap along the curve. Okay, so this is true. And the integral over the line integral over the boundary of S, right? The boundary of S is C1 plus C2. I need orientations for all of this to make sense. So C1 and C2, let's orient like this. The compatible orientation for S is upwards like this. And then for C3, I have to choose some orientation. Let's do it that way. Okay, so for the line integral around the boundary of S, that's C1 plus C2, f dot dr. Okay, well, this is the integral over C1, f dot dr, plus the integral over C2, f dot dr, plus the integral over C3, f dot dr, minus the integral over C3, f dot dr. Right, so I've done a mathematician's favorite trick of adding and subtracting the same thing. So I've added 0. So this doesn't change anything. This is okay. But if we look at C1 plus C3, so what is the curve C1 plus C3? That is C1 plus C3 is this way, right? So C1 plus C3 is that curve. That is the boundary of S1. Okay, and now let's look at C2 minus C3. Well, C2 is this way, and then minus C3, that's C3 but against the orientation, so that's this way. Right, so that's the boundary, the appropriately oriented boundary of S2. So C2 minus C3 is the boundary of S2. Right, so so if the integral over S1 is equal to this line integral, and if the integral over S2 is equal to this line integral, then things add up correctly, and the integral over S is equal to the line integral over the boundary, right? So all this is to say that we can, if we have a big complicated surface, we can split it into smaller pieces and then put the integrals back together afterwards. And just like we did with Green's theorem, the key of proving this will be to split our surface into pieces small enough so that it's very simple. So what is the special case that we will use to prove sort of the base case? The special case of a surface that we will use is where the surface that we're working with is the graph of a function. And we're going to assume that z is a function of x and y. This whole proof just goes through with variable names changed if x is a function of z and y, or y is a function of x and z. Okay, so here's the situation, right? We have this surface that is in 3 space. Its boundary is right here, and since it's the graph of a function, right, we're going to just use the xy plane as our parameter space. So the region of parameter space that we need to get this surface, let's call that R. And then R has its own boundary, which is boundary of R. Notice that the boundary of R is the shadow that the boundary of S casts onto the xy plane. That will be handy. Okay, so given this setup, oh, and just to be concrete, let's suppose that we're traversing the boundary of R in the usual way, counterclockwise. That induces the counterclockwise orientation around the boundary of S, and it induces the upwards orientation on S. If the boundary of S and S itself had the other orientation, well, that would just put a minus sign on both of these, and they'll still be equal to each other. Okay, so let's see what we get for both of these integrals. Now we have a line integral to write down, and we also have a surface integral to write down. Let's start with the line integral. So the line integral around the boundary of S of f dot dr. Okay, this is the trickier one. So we need to parameterize this line integral. So we can do that like this. So first let's parameterize the boundary of R. So down in our parameter space, let's say that is x of t comma y of t. Okay. Now as we do all of this, what is a function of what, like writing out here that t is the independent variable, it will get too cluttered for us to be writing that all of the time. So when I parameterize this, I'm going to stop writing the of t everywhere. This gets especially bad with our vector field, because remember, our vector field is m, n, p, because right, we're in 3 space, so we have 3 coordinate functions, and each of these are functions of x, y, and z. Right? And x, y, and z are each going to be functions of t, so really I need an x of t, y of t. You can see that we're just sort of stacking up so much stuff that it's making it harder to keep track of what's going on rather than easier. So I won't always write out the parentheses and the variables in our parentheses for all of these, but it is very important that we keep in mind that these are here, as we'll see later. Okay, so let's parameterize this line integral. Right, we've parameterized the boundary of R, but that means for our parameterization of the boundary of S, well, it's going to be x of t, y of t, and then z has to be little f of x of t, y of t. I think this is the last time I'm going to be writing out all of the t's. From now on, we'll just have to remember that they're there. And this is for t values in some interval of t values. All right, capital I for some interval. This is some interval from a to b, whatever t values take you once around this curve. Okay, so let's use this parameterization to write out this line integral. So this is the integral over the parameter values that we need, I, and it's f, which is m n p, dotted with the derivative, right? What we need is r prime, and when I say r prime, maybe I should have called this one r. Okay, so we need the derivative of this parameterization, which is x prime, y prime, comma, and now we have to be careful. It's tempting to just write f prime, but f prime doesn't make any sense. F is little f is not a function of t. Little f is a function of x and y are both functions of t. So we have to do the multivariable chain rule to take the derivative of this coordinate function with respect to t. So right, we get one term for each path through this diagram. So we get the derivative of f with respect to x, right? And there are going to be so many derivatives flying around that writing out the partial derivative notation like this, it's too cluttered. So what I'm going to do instead is just use a subscript. So whenever I write a subscript, that is a partial derivative with respect to that variable. So this f sub x, that's really partial f partial x. So partial x times the derivative of x with respect to t, that's x prime, plus, and now the other path, partial f partial y, which we'll write f sub y, times y prime. Okay, all of that dt. So this is our line integral. Now we could leave this how it is, but, right, I mean, this diagram probably makes you think, well, look, why don't we rewrite things in terms of what's happening in the xy plane, because then maybe we could use Green's theorem. Well, that's a good idea, but to do that, we can't leave this the way it is, because right now this integral lives in 3D space because this is a dot product of 3D vectors. So to get this into 2D space, we have to write out this dot product. So this is the integral over I of, so right, x coordinate times x coordinate, so mx prime plus y coordinate times y coordinate. Oh, I missed, no, that's right. Okay, m times x prime plus n times y prime plus p times this whole mess. And I'm gonna multiply out, or I'm gonna distribute this p. So I get p times f sub x times x prime plus p times f sub y times y prime, all dt. Okay, now remember the goal was, hey, why don't we interpret this as a 2D situation? And if we're thinking of that, we should gather up all the terms that have x primes and gather up all the terms that have y primes. So when we do that, we get the integral over our interval of t values of, let's see, for x primes we have an m, and from here we have a p times f sub x, so all of that times x prime, plus n coming from here, plus p times f sub y times y prime, so that's this term here, all dt. And now with the x primes and y primes separated out like this, you can see that this is actually an integral of the vector field m plus p times f sub x, comma, n plus p times f sub y, dotted with x prime, comma, y prime, dt over the interval I. But now this is genuinely a line integral of a vector field around the boundary of our region down in the xy plane. It's a different vector field than we started with, but you know, that's the price of doing all this. So now this is the integral around the boundary of R, the integral of m plus p f sub x, comma, n plus p f sub y dot dr. Okay. And this is because this right here, this is the x prime y prime, this is the derivative of the parameterization of the boundary of R. right? If we remind ourselves the parameterization of the boundary of R, it was just x comma y, and so the derivative of that is x prime y prime, and that's why this scalar integral, or single variable integral, is actually the same as the line integral around the boundary of R. Okay, it's because exactly the right thing shows up here to rewrite it as the integral around the boundary of R. Okay, but look, now this is genuinely a 2D line integral around a boundary, so we could use Green's theorem. Okay, Green's theorem says that this line integral around the boundary in 2D is the integral over the entire region R of the curl of this vector field, dA. And this dA is really just dx dy, right? This is in the xy plane. So we need to figure out what is the curl of this vector field. And remember, this curl is 2D. So what we're going to do is take the derivative of this with respect to x, and then we're going to take the derivative of this one with respect to y. And we need a minus sign. Now when we do this, we have to be careful, because remember, this n has, what is this n a function of? This n is n of x comma y comma f of x comma y, right? So when we take the partial derivative of this with respect to x, right, the situation is we have n, which depends on x, y, and f depends on x and y, right? And x is x, y is equal to y. So when we take the derivative of n with respect to x, there are two ways to get to the x down here. There's this one, and that gives us the derivative of n with respect to x, times the derivative of x with respect to x, but that's one. Okay. And then there's this path, which gives us, so plus, then there's this path, which gives us the derivative of n with respect to f times the derivative of f with respect to x. I'm sorry, I shouldn't have f here. I should have z here. Right? Z is f of xy. So this f should be a z. Okay. So that's just for the derivative of this piece, plus, okay, now we need to take the derivative of this. This is a product, right? And when we take the derivative of p, this exact same tricky stuff happens when we take the derivative of p with respect to x. So we get two terms, not one. We get the derivative of p with respect to x plus the derivative of p with respect to z times the derivative of f with respect to x. All of that times derivative of f with respect to y, plus, right, we're doing the product rule, now derivative of p, or sorry, p with no derivative times f with a derivative, so f sub y, that was the derivative that was already there, and then we are taking another derivative with respect to x. Okay, so that. All right, now we have to subtract, and then we need the derivative of this first coordinate function with respect to y. So, and again, this, every time we differentiate either m or p, this stuff is going to be happening again. So we get the derivative of m with respect to y plus the derivative of m with respect to z times the derivative of f with respect to y. Okay, that's just the derivative of the m part, plus, now we need the derivative of p times f of x, or f sub x. So again, we get, when we differentiate p, we get this stuff happening. So we get the derivative of p with respect to y plus the derivative of p with respect to z times the f derivative of f with respect to y. Okay, all times f of f sub x, okay, plus, and now the other part of the product rule where we differentiate just the f part. So p times f with an x derivative that it already had, and then the y derivative that we're in the middle of doing. Okay, we did it. So let me clean this mess up, get this out of the way. Okay, so this entire thing, it was the line integral around the boundary of s of f dot dr. We got this giant mess. Okay, so pretty unpleasant. Also not totally clear if any of this is helpful. Of course it is helpful, otherwise I wouldn't be doing it, but I mean this looks quite bad. It's not as bad as it first appears, because if you look carefully, right here we have a p sub z, f sub x, f sub y, and here's the same thing, here's the same thing, but with a minus sign in front of it. So these parts actually cancel. So that's something. Not a lot, but it's something. So that leaves us with a p sub y times f sub x, right? Don't forget to distribute this f sub x. And so this f sub y also ends up over here. Okay, so now we need to write down the integral over the surface of the curl of f dot a normal vector d sigma. Okay, so let's parameterize the surface. Well, for the surface, right, we're assuming the surface was a graph, so it's just x, y, f of x comma y. Okay, so to work out n, we need to take the derivative of r with respect to x. That gives us 1, 0, and then the derivative of little f with respect to x. When we take the derivative of r with respect to y, we get 0, 1, and then the derivative of f with respect to y. And when we take the cross product of these, we're going to get, so r sub x cross r sub y is, so minus f sub x, comma, and then this one minus f sub y, and then for our z coordinate we get just 1. And notice that this is pointing upwards because the z coordinate is positive, and that is the orientation that we wanted, right? So this cross product is the cross product that we want. It is pointing upwards. So for our double integral, it's the integral. When we're parameterizing this, right, our parameters are x and y, and remember that way up here, the region in our parameter space that covers the surface up in 3D space, the region in the parameter space, that's just r. So when we parameterize this surface integral, we're integrating over r, and that means that we're going to have dx dy, or just dA. Okay, so now we need to write out what is the curl of f, and take the dot product of that with partial r, partial x cross partial r, partial y. Okay, so curl of f is a big mix of partial derivatives of the coordinates of f. Remember, the vector field capital F is m, n, p. So curl is, let's see, in the x direction, it's the derivative of p with respect to y minus the derivative of n with respect to z. In the y direction, it's the derivative of m with respect to z minus the derivative of p with respect to x. And in the z direction, it's the derivative of n with respect to x minus derivative of m with respect to y. Okay, dotted with this cross product that we just worked out. So minus f sub x minus f sub y, comma 1. Okay. Yes, okay. All right, so let's write this out. This is the integral over r of, So I'm going to, when I do this dot product, I'm going to distribute this piece over this difference. So I get minus p sub y little f sub x plus, because I have a minus minus, so plus n sub z little f sub x. Okay, that's for the x coordinates. Now for the y coordinates, right, distributing minus f sub y over this stuff, minus m sub z f sub y plus, because it's minus minus, p sub x f sub y, and now the z product plus n sub y minus n sub x minus m sub y dA. Okay. All right. Well, if you remember our line integral, we had it written as an integral over R. So now that we have our surface integral written as an integral over R, maybe it's time to compare the two. So let's see. In this one, we have a minus p sub y f sub x term. If we go up to our line integral, there's a there's a minus p sub y f sub x term. Okay, so this one matches n sub z f sub x. There's an n sub z f sub x. So this one we have minus m sub z f sub y. That one's right here, right? Remember the minus sign is over there. Okay, so this one's taken care of. P sub x f sub y. That's right here. Okay, so this one's done. N sub x. That's right here. And minus m sub y. So that's these two, right? So we have everything here. Do we have any extra pieces? It looks like it, but actually look, these two, I should have pointed this out earlier, these two are actually the same, but with opposite signs, and so these cancel. So we have all the same pieces in both of these integrals. So we finally showed that for graphs, for surfaces that are graphs, our guess is correct. The integral, the line integral over the boundary of the surface of f dot dr is equal to the integral over the surface itself of the curl of f dot normal d sigma. Okay, but remember, we already convinced ourselves that that these things all, if we've split a surface into pieces, we can put the integrals back together in a coherent way. So everything adds up correctly. So it's actually not just for graphs. It's actually for any surface where the boundary is piecewise smooth. Right. We need the boundary to be piecewise smooth so that we can actually write out what this line integral means. Okay, so this fact is extremely non-obvious. I think it's maybe the hardest proof we've done in the whole class. This is called Stokes Theorem. Okay, so what Stokes Theorem does, if we go back to our big picture, what Stokes Theorem does is it fills in this gap here. So this is Stokes. So in later videos, we'll look at examples of how we can actually use Stokes Theorem.